Yeah. So this is a series on the artificial intelligence and all the main concepts in it. And in this session, I will be covering the search algorithms. Going to search algorithms. Let's talk about one of the famous ones that we use. That is uninformed search. Now, okay, so let me just explain the way I'm going to structure this series on artificial intelligence. Um, you may have seen, so this is the first video, by the way, on this series. And usually, when we start a subject, we would go through the history or like slight a bit of definition of artificial intelligence and such. Now, this series, I will make it slightly unconventional. So I'll just cover the random topics in slightly. It's kind of like the Quentin Tarantino movies. So that's how I structured it. Like I will do a whole video on just the search algorithms, a whole bunch of videos, and then on another major topic, and then on the other major topics. So you must remember that this is not. So it's not. There will be nothing like part one, part two, such. So let's get started. You will understand it once make a few videos on this. Uh, Search is one big part. Obviously, the search algorithms and these uninformed search algorithms are just search algorithms that don't have any data in advance. They are also called as the blind search algorithms, and they're a class of search algorithms that do not use any domain-specific knowledge about the problem being solved. Again, emphasis on the domain-specific knowledge, and uninformed search algorithms rely on the information provided in the problem definition, such as initial state, the actions available in each state, and the goal state. Now they're called blind because they don't have a heuristic function to guide the search towards the goal. Instead, they explore the search space systematically. Yeah. Yeah. So they don't have any um, domain specific knowledge, but they do have our initial state, actions in each state. Again, this is just overview. Obviously, it may differ. There may be types which have some more information than this, or none of this at all. But in general, they are given initial actions in each state and then a goal state. And also, they're called blind because they don't have a heuristic function to guide the search towards the goal. Okay, there's no heuristic function to guide towards goal. So heuristic function towards the goal. This is also kind of domain knowledge, if you will. So they rely on exploration instead, which is basically searching. This is also kind of an idea you can use to design games, for example. You can have it totally exploratory, you can make it slightly more guided. And in fact, many games like Assassin's Creed do provide you an option in the settings. You can keep it fully exploratory, or you can have some of it being guided to you. Now, uninformed search algorithms provide basic search strategies for exploring problem spaces where no additional knowledge is available beyond the problem definition. These algorithms are important for solving wide range of problems in AI, and they're not always efficient, but they do provide a baseline for understanding and solving complex problems in AI. So now there are the many types, obviously. Let's just go through a few of them here. Let's talk about breadth first search. Now, may have studied this elsewhere in a subject called algorithms and data structures, or just algorithms. Nonetheless, for for someone who is studying purely artificial intelligence, this would be the first time you're seeing it. Now, breadth first search explores all the nodes at the current depth before moving on to the next level. It uses a queue data structure to keep track of nodes, ensuring that the shortest path is found in an unweighted graph. To just visualize it, what it does is, let's say you have nodes like this. These nodes as edges, and it goes like that. They could all be connected, and like that. So goal could be somewhere else now. Unlike depth first search, which is another close related algorithm, this one um, searches all of its neighbors. So this example would this one would go here, and so here, no, not that one. Search here, here. So all the close related ones it will first search. Depth first search would do something else. It would do something like would go the depth first. So if you consider this, I would go to depth and then come back, and then another to its depth and then come back, and then another depth. So this is the kind of the distinction between breadth first and the depth first. Now, this kind of guarantees, not kind of, it does guarantee the shortest path if the cost is uniform. So let's say the cost means the information required to the cost is uh, the value assigned to this edge to go from here to here. The cost. Now, if the cost is uniform, meaning all of the cost doesn't matter. Maybe only takes like 1 unit, something like that. If cost is uniform, then you can get the shortest path with this algorithm, guaranteed. Now it does use more memory because it has to store all the child nodes. But yeah, and this one does use the queue as the data structure, the primary data structure, and the BFS function finds the shortest path in a 2D maze using breadth first search algorithm. It starts from a given position and explores neighbors up, down, left, right. A queue stores positions along with the path taken. A visited set prevents the revisiting the positions. If the goal is reached, the function returns the complete path, otherwise it returns none. Visualize maze function displays the maze and found path using matplotlib. Okay, we might be getting a little ahead of ourselves, but basically it's not that complicated of an algorithm. Depth first search I have just explained to you. It goes to the depths first. And regarding the full algorithm or the full code of it, might get into them in other videos, or should I cover them now? Thinking about it. Okay, let's not get into the given how famous these two are, especially. I'm not going to the actual implementation of them because pretty guaranteed you will find I might have already covered it because that's how famous these two are. I did visualize it here, so let me go to the next one. Okay, just to give some more details of the depth first search. Well, instead of the queue, use it in the so again the breadth first search uses the queue, but the depth first search uses stack mainly. You could use any stack here or queue here as well, but for the best implementation, you would use a stack for this first search, and it's kind of more memory efficient than that first search, but it does not guarantee the shortest path. So and this guarantees shortest path. So this doesn't give the shortest path. More memory is requires less memory, and yep, so those are the important things to know. Now there's a depth limited search as well. Depth limited search, DLS. It's a variation of depth first search that limits the depth of the exploration to prevent infinite loops in larger infinite search. So can get stuck in infinite loop. This limits that very thing. So let's just say you have that. So instead of going all the way in, it will stop itself at, let's say, the second level. It will not go any further than that. So it's useful when the goal depth is known. If your goal is supposedly can reach a third level, 3 levels deep, then you can do this. But if that's not the case, then this is not that useful. Into fourth, there's iterative deepening depth first search. Iterative deepening depth first search. You can pretty much tell everything from the name itself. It does iterations instead of recursion, and it deepens every time. So this depth is increased in every look. Now this is kind of like a combination of breadth first search and depth first search. So this is like BFS plus DFS, because remember too that depth limited search is also like BFS, only instead of single depth. So this is like BFS, but breadth being customizable instead of just being one. Being anything, so that being one or more. So in iterative, you do the same thing. Let's say it has all that network. So let's say you go one level deeper, you're not satisfied, you go further deep in another iteration, and you go deeper and deeper in each iteration. That's how this works. Now this ensures completeness and optimality, like the breadth first search uses less memory like the depth first search because it has combination of both. Now coming to uniform cost search, you say as uniform cost search. It extends the breadth first search by considering path costs. So breadth first search considers the path costs are all unit costs, but this one extends that by considering the path costs, which need not be a unit or fixed. It need not be fixed cost. It just expands the least cost node first. Okay, this is just extension of BFS for non-fixed cost paths, and always expands or begins exploring on the least cost node first. That means exactly what you think it means. If we have all these options and if this is the least cost, it will go here first. Now, and then it will go to the next least cost, and then the maximum least cost last. Now this guarantees finding optimal path when all costs are non-negative, you know, or costs given are costs greater than positive, non-negative, and it is slower than BFS, however, because in BFS you don't have to worry about the cost, but here you have to worry about the cost at each step, especially in uniform cases. Because if the cost is uniform, you're better off just use BFS because it's a waste of time comparing them all. Obviously. So, and this does use heap, uses heap, also called as priority queue. And that's about it. Those are the some of the um, uniform search algorithms, and there are various applications, of course. For example, these can be used in pathfinding, for navigation systems and robotics to find the shortest path between two locations, and it can be used in puzzle solving. Let's say something like a 8 puzzle or a 15 puzzle to determine a sequence of moves leading to a solution. They're used obviously in games and also used in web crawling. BFS is widely used in web crawling for indexing. So like, for companies like Google, they do like to index a whole lot of the web. Now that we have covered the uniformed search algorithms, let's look at informed. I'm sorry, we looked at uninformed search algorithms. Now let's look at informed search algorithms. Now, obviously, these are just let me cut this. So, like in uninformed search algorithms, here we do have the domain knowledge. It's just everything that the uninformed doesn't have. This one also has the goal and how to reach the goal and all that. Let's get into this. So these are the search algorithms in AI that use extra knowledge called heuristics to prioritize which paths to explore. So we do come with heuristics. You know, they have heuristics unlike uninformed algorithms to prioritize which paths to explore by estimating how close each possible step is to the goal. These algorithms can find solutions more quickly, efficiently than uninformed applied search algorithms. Now, again, in the real world is neither fully informed nor fully uninformed. These are just classifications we make for our ease of doing things. And on a narrow level, of course, these are much more applicable and useful, and it's important to know all this to develop the sophistication required to reach the level of your general artificial intelligence, or something which is more generalistic than narrow use cases. Now, let's get into some of the popular ones in this one. For the first ones would be the greedy best first search. Greedy best first search always picks the next step that looks closest to the goal. So it's greedy. It uses a heuristic, which is a guess which choice the best. It tries to reach the goal as quickly as possible, which but doesn't guarantee to find the shortest path. So picks next step closest to go. Again, this is rather simplistic, don't you think? If you were to live life like this, you would lose a lot of nuance. There's much more to attaining goals than just to look at the next closest step. Of course, on a higher level, it does make sense, and this is in fact very useful in a lot of cases. Things are much simpler, but of course, it's not a free lunch. There's no free lunch theorem. As the no free lunch theorem says, if you have seen my series on the deep learning, there's not one single or simple algorithm that applies for everything. Maybe unless it's transformers. I don't know. Nonetheless, this is how that works, and the advantage. So okay, so There's no guarantee that it finds the shortest path. Guarantee of finding shortest path, because obviously, let's just say this is a long path, but it only requires two steps to the goal. But there's a short path, but it actually turns out to be the longest. So this dumb algorithm has picked this one instead of that one. It uses a priority queue in heap, or also called as a priority queue. And yeah, that's about that. If we go to the second one, we call this A star search. Now, A star search finds the shortest path by combining two things. So finds shortest path by two things, which is how far we have already gone in the case of how far it is left to go. How far we have gone and far left to go. Not just the next smallest step. Like the greedy algorithm, this checks these two things. It checks both actual progress and the potential, so it's very reliable. If our guess the heuristic is good, these are kind of like metaphors or suggestions for life in a way. The greedy method, you just pick the next best step that gets you closer to the goal. It is applicable in a way. The A-star search is slightly better than greedy search. You look at your life, how far you have come, and how far it's left to go, and decide based on that. This checks both actual progress and potential, so it's very reliable if our guess is good, and it uses a combined cost function. F of n equals g of n plus h of n. The which is just the actual path cost so far, how far you've come so far, and then cost to the goal. You know, so if this were the g of n and a heuristic, then this will calculate both. The advantage is that which is this is complete and it's optimal. You know, this is a complete and optimal algorithm when using an admissible heuristic. Now these are some concepts. Okay, what is a complete algorithm? Well, let's see. This is the algorithm in optimal mean. Now it's complete because it's guaranteed to find. Complete means it is guaranteed to find a solution if it exists. Optimal means it is guaranteed to find best cost, which is the lowest cost. Lowest cost, which means optimal solution. Admissible is another concept. That means never overestimates. Now, heuristic is admissible when it never overestimates the true costs to reach the goal. Means you can admit it. It never crosses the line. These are actually important definitions. So this is similar to greedy, as you saw, only it calculates two things instead of one. Now the next we'll look into is beam search. So beam search keeps track of only a set of the best looking options at each step. It moves forward with the best few options and ignores the rest, making it faster and lighter memory, but it might miss the absolute best path. So it's kind of like if you have like this, say many paths, call this beam search. It only tags, let's say, two, so that's the beam, and from here it will look at these two, and from here to that's how it will find the path. Now it has reduced the okay, so keeps track of only a set of this set number of the best looking options. Only number of best options at each step. It moves forward with the best few. Which moves forward with the best few and ignores the rest. Now it has reduced memory usage. It's effective in larger combinatorial search spaces, and it may miss the optimal solution. And yeah, that's it. Is beam search. It is complete, optimal, or what is it? Well, it's not complete. It is not complete and not optimal. No guarantee of it may be the best solution. It is fast enough. If it's not complete or optimal, obviously it cannot be admissible either. So, not optimal implies not admissible also. And the applications of informed search algorithms are that these are used in pathfinding in navigation systems, games, robots, and all that. And the advantages are that you can get the solution faster because obviously you know that so you have some information about the domain and you can adapt quicker to the domain because of the same reason. And there is potential for optimality, higher degree of optimality than that than the uninformed ones. There is a flexible resource usage and it's scalable. The challenges do exist here because it all depends on the heuristic accuracy. If your heuristic is not good enough, you may end up worse than uninformed search algorithms. And because of the extra function heuristic, the memory usages may be high, and there is in order to get the heuristic itself, you will spend a lot of time and computation costs. That's that. And now that we have looked at all those, let's look at the third main thing. Adversarial search algorithms. The adversarial. What's adversary? Well, adversary means your opponent, someone who could get in your way in your life or in your achieving your goal. Someone who could be expensive to you, could destroy you, could be harmful to you. That is an adversary. There could be conflict. There could be an opposition. And the term adversary comes from Latin word adversas, which means adversarius, which means opposed, opponent, adversity. And adversarial search algorithms are the backbone of the strategic decision making in artificial intelligence because, come on, the real world is highly adversarial. There's a lot of life and it's all competing for, for survival. This is the backbone of strategic decision making in AI. It enables the agents to navigate competitive scenarios effectively. So let's look at it. Now, this is a well suited approach in a competitive environment where two or more agents have conflicting goals. Okay, when in an environment where two or more agents have conflicting goals. This family use this to earn more agents. Conflict occurs because they're both wants to go to the same thing. Which how can it be possible? That's the conflict. That conflict arises. And especially when the situation is a zero sum game, which means a good for one player is bad for another. You know, zero sum game. As Peter Thiel says famously, competition is for losers. Uh, as real as this is, um, the success is only possible when you don't think like the. Again, I'm talking about philosophy or like on a higher level here. As real as the world is a zero sum place, and this is especially true when the resources are limited, when the knowledge is not much. When we go to, let's say, like when we settle on Mars, let's say, and the resources are all fully limited. Let's say we have like four oxygen tanks and some other things like that. Well, then it's a zero sum game. But usually, in a modern world, this is an age of abundance. This is an age where we will be able to think broadly, so that those situations may not arise, hopefully. And also success, like when the survival is not threatened. Obviously, when the survival itself is threatened, then Peter Thiel's suggestion will not hold up, because then you have to think about competition. You really have to get that oxygen tank for your family, otherwise your family is going to die. So yes, competition is for losers unless survival itself is threatened, unless it is a sum game indeed. Now, of course, as of today at least, the the knowledge, information, resources, they are seemingly abundant, and any way to think in a competition mindset way is actually counterproductive, not helpful at all. So largely, as far as we as far as the world stays like this, as far as it's not really on the extremes, competition is indeed for losers, and it's not a zero sum game at all. It is a pie that can grow. Economy is a pie that has been grown objectively since many decades, almost maybe 2 centuries since. And yep, that's a bit of philosophy and actually some important information. These kind of insights from different fields can actually be helpful. Okay? They can actually provide you insights into these things. There's a field as big as AI. It can definitely have insights from all the other fields. Anyways, going back to the algorithms. Adversarial algorithms are especially useful when there is a no win-win situation. Win-win is not possible. There's a win-lose, a lose-win, lose-win. It's a zero-sum game. And the artificial intelligence adversarial search plays a vital role in decision making, particularly in competitive environments associated with games and strategic interactions. By employing adversarial search, AI agents can make optimal decisions while anticipating the actions of an opponent with their opposing activities, objectives. It aims to establish an effective decision for a player by considering the possible moves and counter moves of opponents. The adversarial search in competitive environments can be utilized in the below scenarios, where a system can assist in determining the best course of the action by both considering possible moves and counter moves of the opponents. So, uh, the role of adversarial cells obviously they are used in game playing or any other decision making algorithms where strategic thinking, evaluation of potential outcomes, and all. Well, those are where all that is required. Now, there are several algorithms. I mean, okay, so the search algorithm which we saw just depth for search, breadth for search, greedy, best for search, A star. They are well suited for single agent environments where there is no direct competition or conflict between multiple agents. Exactly. They are non-adversarial, but in adversarial, those don't work. And there are two main algorithms: the min-max and alpha-beta pruning, which is exactly what we'll be looking at now. Come to Minimax, Minimax, not Miramax, the movie producer. Minimax algorithm is claimed to be a recursive or a backtracking algorithm that is responsible for choosing the best optimal move in the conflicting environment. Minimax algorithm operates on a tree structure known as the game tree, which is the collection of all the possible moves in the corresponding game states in a given game. The game tree's leaf node accommodates all the possible moves. The game state denotes the current board direction condition. With every single move, the game state changes. The game tree gets updated height-wise. And so this is kind of like what you might have seen in movies, where let's say the heads-up display of your robot is updating the information every second. So it goes like this: that all the possible states. So it updates again the next state when something moves, and then it updates like that. So that's how the tree would look like. So, some of the important terms here would be like the minimax tree, the tree structure which shows all possible moves, and the game states in the game used by the minimax, and the max, the maximizer. The maximizer seeks favorable outcomes in games by maximizing chances of winning for themselves as players. Minimizer reduces winning chances, making moves leading to least favorable outcome for maximizer in games. Again, maximizer maximizer seeks favorable outcomes in games by maximizing the chances of winning for themselves as players. Minimizer reduces the winning chances, making moves leading to least favorable outcomes for the maximizer in games. Why is minimizer needed? Isn't it contradictory? Let's say. Well, there are some of the other terms are that there is an initial state, there is a terminal state. Terminal states are the final outcomes of a game board, resulting in either a win, loss, or draw. There is the heuristic evaluation function. Exactly, the heuristic. It's back again. The heuristic that evaluates the game states for maximizer, assigning numerical values to each game state based on piece positions and material advantage and board control and that stuff. So, how does the minimax search algorithm help in finding the optimal strategy? Well, there is a terminal state. The minimax value of each state in the game tree can be used to determine the optimal strategy. The minimax refers to the utility of being in that state that assumes both players play optimally from there to the end of the game. Again, the minimax refers to the utility of being in that state that assumes both players play optimally from there to the end of the game. That's the terminal state. In a non-terminal state, when the max term arrives at the game, max aims to move whatever leads to the state of maximum value. Min, min moves whatever min prefers to choose the move that leads to a state of minimum value. So in a way, you can have minimax given a state of S. You have utility takes a small s and max if it is terminal. If it's a terminal state, otherwise max A belongs to the actions of S, maximum of the mini max, which takes the result as A if to move S equals max. Well, it's pretty long. Min of A belongs to actions of S max max A if to move of S equals min. To reiterate, the pseudocode goes like this. The minimax, which takes node depth and maximizing player as arguments, this function recursively evaluates the minimizing value of each node in the game tree. It alternates between maximizing and minimizing player nodes based on the maximizing player parameter. There's also the function find best move of the board, which is responsible for iterating through all the possible moves on the board and evaluates each move using minimax algorithm. It then turns the moves to the highest minimum value for the maximum player. Uh, in order to understand this, uh, you need to know that this is a backtracking algorithm that recursively tries different possibilities and backtracks when the solution is not found. In the context of minimax algorithm, this involves exploring all possible moves in the game tree that evaluate each potential outcome and making decisions based on their evaluations. And also there are two players such as the maximizer and the minimizer. The maximizer aims to maximize the score by winning the game, and conversely, but the minimizer aims to minimize the maximizer's score by preventing the minimizer from winning. So the maximizer is trying to maximize the score. The minimizer is trying to minimize the maximizer's score. Not just minimizing the score, it's minimize the maximizer's score. If you take the example of decision making, um, So the time space complexity, if we talk about the minimax algorithm, explores the complete game tree using depth first search approach. You know, so depth first search, and time complexity is like O of big O of B to the power of M, where B denotes legal moves at each point. Mem is the max depth of the tree. Now this algorithm arises because at each level of the tree, the minimax algorithm must consider all B legal moves and the process repeats recursively for M levels until the terminal state is reached. Now space complexity is also big of E of M. Now with that over, let's go to alpha beta pruning. What is pruning? Pruning algorithms, they are constraint minimization algorithms. You're pruning the constraints to make your problem easier. Alpha beta pruning is an optimization technique for minimax algorithms. So it's just an optimization technique for minimax algorithms. It reduces the computation time by a huge factor, allowing the user to traverse faster and deeper into the tree. Stops evaluating when at least one possibility has been found and typically moves to more worse than the previously examined move. Again, it reduces competition by a huge factor because it allows the user to traverse much faster and deeper into the tree. It stops evaluating when at least one possibility has been found and typically proves the move to be worse than the previously examined move. Minimax search is so kind of like slightly smarter than Minimax, and while the Minimax is based on depth first search, it considers nodes as along the single path tree. Alpha beta pruning bounds the two major parameters max value, the state alpha beta representing alpha plays maximizer row, whereas beta plays minimizer row. Alpha here denotes the value of the best or highest value. Beta denotes the value of the best or the lowest value. Why exactly is this effective? Well, this is okay. That's the new information. So this is effective. Okay. Algorithm. Why is it effective? Well, there's branch elimination is effectively pruning. You know. Okay, we didn't talk about. So okay, we didn't talk about that. This is okay. This is complete. Okay, it's optimal, but it's not admissible. So can potentially find it. There's a guaranteed solution, and there's a guarantee that it can find the lowest cost solution, but it can overshoot. The same for the alpha beta pruning because it's basically the minimax. search algorithm. So it is complete, it's optimal, not admissible. Now again, admissible is just not applicable here because it's for a heuristic search, not game tree algorithms like Minimax. It's for only heuristics, no, it's not, okay, not applicable. And so why is this effective? Well, the alpha beta considers branch elimination, and we are pruning the branches, like just like you prune a tree. And there's also the branch and bound. The alpha beta is based on the branch and bound method, which offers a way to solve optimization before automation problem by dividing them into subproblems. Uh, and there are heuristic improvements to limit the computation time. So, how do you understand this? Well, the game trees can hold bounding branches that can lead to different game states, and implementing alpha beta pruning in such game trees can help prune away the branches if already exist. If there already exists a better move, this makes the algorithm computationally efficient. Since there is no need to search other branches, if there already exists a better move in the game tree. At any node in the game tree, the maximizing player is used to store the maximum score in the alpha, which assures that the max node contains only the maximum scores. Similarly, the minimizing player is assured of minimum value, which is stored by the beta. These two values of alpha and beta are updated and maintained by the algorithm. Now, we will go into uh, the pseudocode of the algorithm and implementation and such details. The actual, again, in this video, we clearly haven't gone into pseudocode for any of this because that would obviously take a lot more time. This is more like an overview, and we'll go into pseudocode perhaps in later sessions. Again, in modern days, pretty much all the pseudocodes are available anyway. It's more important to understand what these mean than knowing the. It's more important to understand what all this can do, and having an understanding of all this than knowing all the low-level implementations. Because again, intelligence, memory, guys, these are no longer the these are no longer the uh, things that will distinguish you. So you have to be like faster, more optimal than that. If you memory and intelligence, by intelligence I mean the like raw intelligence is no longer the distinguishing factor as of now. If you have seen how far AI has come, so we are pruning effectively uh, anything that doesn't exactly help us immediately, or at least for the sake of being time efficient. I am skipping those. Anyways, with that, uh, the applications of these adversarial search algorithms is that they're used in board games, game theory, and puzzle solving. Game theory is a unique algorithm of evolution, look up the cellular evolution and such things. And yeah, I mean, these are basically all the majority of the search algorithms. There's definitely much more than this. They will try to cover perhaps in something like a search algorithms part 2. Maybe we'll dig a little deeper if that's possible. And for now, this is about it.